Welcome to This Explainer. Okay, today we are exploring the absolute foundational building blocks of modern mathematics. If advanced math has ever looked like a total alien language to you, well, today we're learning the alphabet. The text we're exploring today makes it super clear. The concept of a set is required for almost every single branch of mathematics you can possibly think of. From mapping out the rules of complex geometry to calculating the probability of a future event, sets are literally the framework of our mathematical reality. And it all starts right here. Our source text highlights this incredibly profound quote from the mathematician G.H. Hardy. He says, "In these days of conflict between ancient and modern studies, there must surely be something to be said for a study which did not begin with Pythagoras and will not end with Einstein, but is the oldest and the youngest." We're about to learn a truly timeless language, guys. It's a way of organizing the universe that is ancient in its logic, but completely modern in its application. Okay, let's dive into this. We're going to master this potentially intimidating math chapter in 5 logical, simple steps. We'll cover what a set is, meet Georg Cantor, look at empty and infinite sets, explore subsets and intervals, and finally learn how to operate on sets.
Step 1. What exactly is a set? It is the ultimate mathematical building block.
Now, what's really interesting about this slide is the stark contrast between what is just an everyday collection and what mathematically qualifies as a strict set. On the left side, we have the vowels in the English alphabet, A, E, I, O, U. That's a concrete fact, right? Anyone in the world, if asked, is going to give you that exact same collection. That makes it a well-defined collection, which means it's a true mathematical set. But look at the right side, the 5 most renowned mathematicians. I mean, my list might look very different from yours. Subjective criteria vary from person to person. Because it's not universally verifiable, it is not well-defined, and therefore it's absolutely not a set. Because sets are so incredibly foundational, mathematicians use a specific shorthand. Think of this as your handy reference guide to the nouns of our mathematical language. When you see a capital N, it just means the set of all natural numbers. Z stands for all integers. Q represents rational numbers, and R stands for all real numbers. Oh, and if you see a little plus sign next to them, like Z+, it just means we're only looking at the positive versions of those numbers. So don't let these letters intimidate you when they pop up in equations later on. They're really just efficient abbreviations for massive, well-defined collections. Moving on to step 2, let's meet Georg Cantor, bringing a little human element behind the math. So this is the German mathematician Georg Cantor, the guy who actually developed the theory of sets as we know it today. And our text has this really great detail about him. Cantor didn't just sit down one day and decide to invent set theory out of thin air. He actually encountered sets almost by accident while trying to solve incredibly complex problems dealing with trigonometric series. He basically realized he needed a brand new structural language to explain what he was seeing. Necessity truly is the mother of invention, right? All right, step 3, empty and infinite sets. We are embracing mathematical nothingness here. First up, we have the empty set, represented by the symbol phi. By definition, this is a set which does not contain any element whatsoever. It's kind of funny if you think about it. Mathematicians created a specific, profound symbol just to describe a completely empty box. But it's absolutely vital for making mathematical logic work flawlessly. So the crucial point is understanding exactly how a set becomes empty. It happens when we create impossible conditions. Let's walk through these paradoxes straight from our text. First, an even prime number greater than 2. Well, the only even prime number is 2, so anything greater than 2 is literally impossible. The set of those numbers is completely empty. How about an odd number where x squared equals 4? Well, 2 squared is 4 and negative 2 squared is 4, but neither of those are odd. It's a logical dead end. Evaluating that condition yields an entirely empty set. Now, jumping to the totally opposite extreme, we have to define our limits. A finite set has a definite countable number of elements. For instance, if our set is students currently studying in class XI in a specific school, we could physically go to that school and count every single student. It might take a while, but it ends. An infinite set, however, has absolutely no definite limit. The set of natural numbers is uncountable. You can always add one more. Step 4, subsets and intervals. We're looking at layers within the universal set. Let's move to and see how this builds upon itself, using the shorthand we just learned. Think of subsets kinda like mathematical Russian nesting dolls. If every element of set A is also an element of set B, then A is a subset of B. Look at the number system. The natural numbers, n, fit perfectly inside the set of all integers, z. The integers, z, fit perfectly inside the set of rational numbers, q. And all of those rational numbers fit snugly inside the massive set of real numbers, r. N is a subset of z, which is a subset of q, which is a subset of r. It's just a wonderfully elegant hierarchy.
When we're dealing with subsets of real numbers, this simple bracket notation visually communicates our rules. If you see round brackets and open interval, it means the n numbers are excluded, meaning y is strictly greater than a and strictly less than b. But if you see square brackets, a closed interval, it means those endpoints are actually included. It physically represents the boundary right there on the page, making the length of the interval super simple to grasp. But hey, before we can start combining all these sets, we need a sandbox to play in, right? This is the universal set, denoted by capital U. It's the basic, overarching set relevant to whatever specific context we're studying. For example, if we are analyzing subsets of human population data across different cities, the universal set is, quite simply, all the people in the world. It provides the ultimate boundary for whatever scenario we're presently analyzing.
Finally, step 5, operating on sets. These are the verbs of set theory. We have the vocabulary, and now we are finally ready to take action. And this brilliantly illustrates the distinct mechanical difference between two vital operations, union and difference. On the left, a union, represented by that U shape, is a complete merger. You're taking all the elements from set A and combining them with all the elements of set B to make one giant set, just making sure to only write down the overlaps once. Now on the right, the difference, written as A minus B, is an extraction. You're taking set A and surgically removing any element that also belongs to set B. One brings collections together, the other pulls them apart.
I want to wrap up this explainer with a brilliant brain teaser pulled straight from the advanced exercises in the chapter. Imagine you have two sets, A and B. If you merge them completely together, their union, and the result is exactly the same as if you only kept the elements they have in common, their intersection, what must be true about sets A and B? Think about it for a second. If combining everything gives you the exact same result as only keeping the overlaps, the absolute, flawless mathematical truth is that set A and set B must be the exact same set. A equals B. It's perfect logic, stripped of all ambiguity. But it leaves you wondering, if this mathematical language can prove two seemingly different things are entirely identical, what else in our universe can this logic decode? Keep exploring, and thanks for joining me in this explainer.